Okay, so let's continue with sedimentation. We'll finish this today. So what I want to look at today is more of the design aspects. We've looked at type 1, 2, 3, and 4 settling. We've looked at how do we predict removal efficiencies for type 1 and type 2, and discuss the fact that type 3 and 4 are much more difficult to estimate or predict removal efficiencies because of the interactions between flak particles. So this is a conventional circular clarifier. Okay. So what you can see here is water enters typically through the middle, and there's often a middle compartment here. For instance, in the East Lansing plant, they have a secondary clarifier, softening plant. So they have upflow clarifiers, and then the water goes into a secondary clarifier, and there they actually add ferric chloride. And that's added because of the organic matter that is introduced from the water, they recycle water from the sludge lagoons. That has a fairly high organic matter content. So they add ferric chloride to remove that NOM. It's not necessarily the case in all plants, but this is what they do in the East Lansing plant. So the sludge settles to the bottom, and typically you've got this sort of a scraping mechanism on the bottom that scrapes the sludge into a hopper in the center, and then there is a sludge pump here, and that pumps sludge to any secondary processing that is accomplished. Typically these have a sloped floor, and then typically you're not pumping continuously. You monitor the amount of sludge buildup, and then the sludge pump is turned on, and then you're pumping sludge into the next process. This is a horizontal sedimentation basin. What you see here is typically these have a chain and flight mechanism, and what you have is you have a mechanism. You can see here there's actually this is a scum trough. Sorry, that's the effluent weir. But often there is a scum trough here, but what happens is this mechanism circulates like this, and sludge then is pushed from along the bottom. So you've got on this flight, you've got some sort of essentially sort of feet that push the sludge into this hopper. Why is the hopper in the near the inlet? So here's my inlet, here's my effluent weir. This doesn't show the scum trough, but here's my effluent weir. If the water is flowing over these weirs into the launder, it flows then into a main channel and then on to the next process. So typically in a water treatment plant, that would be filtration. Why do we have the hopper in the inlet, near the inlet? Why not on the other end?
So because that's where the dirty water is coming in?
Okay, one, you're absolutely right. Okay, so the dirtiest water is coming in here. And the effluent is obviously the cleanest. And then you've got your sludge that's collecting in this hopper. Okay. The other issue has to do with turbulence. If you have your hopper at the effluent's end and you have turbulence introduced because of the hopper, what impact is that going to have on the quality of your effluent?
Could it stir up some of the sludge and then get it into the effluent?
Exactly. So it potentially stirs up the sludge. That sludge ends up in the effluent. And as a result, you've got diminished quality. On the other hand, if you have turbulence at the inlet end and you stir up some of that flock coming in, what impact does that have on the effluent quality?
Shouldn't really have much.
Exactly, it shouldn't have much. So for that reason, the sludge hopper is always at the inlet end of the tank. Okay. The basins, in this case here, you've got your launders running parallel to the flow. So the flow is in this direction, and you can see the launders, and then the water, as I mentioned, is flowing over here into a central channel here, and then out. So for instance, in the East Lansing plant, they have circular clarifiers, but the water then flows. It actually flows under the floor into the filtration room. We can also use high rate settling. And this is used where we need to increase the settling capacity. So for instance, we're not getting sufficient settling, or the flow rate has increased significantly, and we either don't have the space to add another unit, or we don't have the funds to build a whole nother system. So this question just asked, what is the sludge hopper? The sludge hopper is simply this region here. It's basically think of it as a smaller basin within your larger basin, and that's where the sludge collects. And from that, you've got a sludge pump. That sludge pump is periodically turned on, and sludge is pumped from there to the subsequent process. What is a launder? I'm just going to skip over a couple slides just to, okay. This unit right in the center is your launder. So think of it as a open channel with weirs on the side, and that is allowing the water to collect into that weir, and then it would be transported to a central channel. This is another launder. This is actually in the one on the picture on the right. That's the launder. It's in the secondary clarifier in the East Lansing plant. And this is different. This is the one on the left is a notched weir. And you can see on the right, these are just an orifice, and water flows from the surface of your tank into this open channel referred to as a launder, and then into the main channel. And I don't think I have a photo of the main channel. I was just, if I had a photo of the main channel from the East Lansing plant, I don't. So the way this works is the high rate settler, back to the high rate settler, is that a high rate settler looks like this. So it's a multiple tubular channels sloped at an angle of 60 degrees. And that is used because you get increased settling you get reduced settling times and it increases your area significantly. You can see it here. If this is the sedimentation basin here, and you add these tube settlers, you've increased the effective area by a very significant amount. I've got a video. It's just a short demo of a tube settler.
In this device are filled with water and particles that are slightly denser than water. Notice that the particles in the tube that are vertical settle out much slower than the particles that are on the 30-degree slant. Just to be sure that there's no funny business here, we're going to flip it around and show that they settle out the same way when the tubes are in the other direction. First, we mix them up very well, and then we set it down. Again, the tube that is vertical settles out much slower than the particles that are settling onto a 30-degree slope.
So what just happened there? We've got a tube settler here, and on the other hand, we have, this is the other tube here. Okay.
Did it reduce the effect of the buoyancy force from the water?
Doesn't affect the buoyancy force because it's the exact same material. Think about this. Here's my particle. That particle, and here's my particle entering here. This particle only has to settle this distance before it hits the floor of the tube settler. This particle has to move that entire distance. Exactly right. The particles don't have to travel as far to settle. So the tube settler is much more effective than a conventional settler. So what you'll see in the photo here, this is actually, you can't see it, but this is actually a bank of tube settlers that were added to the treatment plant in Flint. And these were added because, as I mentioned, you can retrofit an existing tank. You fit the tube settlers right in the tank itself. So the cost of that retrofit is much less than the cost of building either a larger tank or another tank. You can also operate at a lower or a higher overflow rate, so you can process more water in the same amount of time. Often, because of the effectiveness of these high rate settlers, you can decrease the amount of coagulant dose. So if you can decrease coagulant dose, what impact does that have on plant operation?
Makes it less expensive.
Exactly. It's less expensive both for the cost of the coagulant and the cost of sludge processing and disposal. So that has a significant impact. So you'll find that in terms of retrofitting, these high rate settlers are extremely beneficial. You can put them in new if you're building a new plant, but many of the plants that we're working on now are really retrofits. They're plants that were built in the 1970s. They're still operational, but we need to upgrade those. This table is from the FE reference handbook. Try to use those throughout just to give you a sense of the type of material you will have available when you take the FE. The Great Lakes Upper Mississippi River Basin, or 10 state standards, set a minimum of 4 hours residence time in your sedimentation basin. This is for water treatment. So you can see here, you see for alum or ferric chloride, It's typically 4 to 8 hours, but the GLEM standards, minimum of 4. You can reduce that to 2 if you're using softening. So the question is, okay, looking back, let's just look back here at the tube. So the sediments in the tubes will settle faster in the tube. No, they actually still settle faster. And I kind of saw that in that video. Once they hit the floor of the tube settler, then they very rapidly move down, slide essentially down the tube to the floor of the basin. So it actually does significantly increase the settling time, because it's only, we can kind of see it here. Okay, it only has to settle this short distance, and then it's going to fall down here. And then once it hits that floor, then you're going to also get flocculation, and you're going to get larger particles. So it will allow it to form larger particles, which will also settle faster. So for your mini design, you won't need to do it as much for mini design 1. You should be looking at the GLEM standards. You can use the 2012 GLEM standards. There's a 2018 GLEM standards, which I have, but I had to pay about $13 for it, and I'm not allowed to circulate it. So while I was hoping we could move to the 2018 standards, let's just stick with the 2012 standards. There aren't significant changes in terms of the major design. But this just gives you some sense of the hydraulic residence times or detention times in these basins. The data here, again, gives you some additional information. And when we talk about weir loading, what we're talking about is the flow. So we have AQ divided by the length of the weir. So this here is flow over length. And it's the length of that weir. Doesn't take into account the notches. It's just simply this length right here. And you can see that we have various specifications, both for water treatment and for wastewater treatment, that 20,000 gallons per day per foot corresponds to 250 meters cubed per meter per day. And that meter is the length. Okay. Now we also have some upper limits for sizes. Why would we have an upper limit for the size? Can we just make these as big as what? Why would we have an upper limit? Many of your clarifiers, especially in wastewater treatment plants, are outside. The larger the diameter, the more wind impact currents you will get, and that's going to affect your removal efficiency. So for that reason, it's really basically one has to do with just the size of your basin, the size of the walkway, because you need a walkway out to the center. So it has to do with that. But it also has to do with the fact that many of these are outside, and you can get wind-induced currents. And at about 200 feet, those wind-induced currents can become quite significant. So we looked at the weirs before just so that I had a sense. Again, as I mentioned, this is an orifice type. These are notched weirs here, and the water is flowing over that weir into the launder. I'm going to have you try and work through this problem in small groups, and then we'll work on this together. So what I am going to do is set up the breakout groups. All right, I think most everyone is back. So just kind of walk through this. So initially, let's just look here. We've got two sedimentation tanks that operate in parallel. Two sedimentation basins. They're operating in parallel. And you're told that the combined flow to the two tanks is 0.3 cubic meters per second, which means the flow to each tank is 0.15 cubic meters per second. So that's the first thing we need to think about. And then you're also told that the tank has a depth of 2 meters and each tank has a detention time of 1.5 hours. So let's convert Q from 0.15 cubic meters per second. What did second. 3,600 seconds per hour, and that equals 540 cubic meters per hour. So most of you got that. A few of you forgot the fact that you have two parallel tanks with a combined flow of 0.3. Okay. You're then asked for the surface area. So let's calculate the volume first. So the volume of the tank is equal to my detention time times flow. We said the detention time was 1.5 hours and my flow rate is 540 cubic meters per hour. So I have a volume of 810 cubic meters. My surface area is equal to my volume divided by my depth, and that is equal to 810 cubic meters per second, and we had a depth of 2 meters, so that is 405 cubic meters per second. The overflow rate is equal to the flow rate divided by the cross-sectional area, and that is 410 cubic meters per hour divided by the surface area that we just calculated. And that is equal to 1.33 meters cubed per hour per meter squared. And that is equal to 32 meters cubed per day per meter squared. You'll also see this written as meters per day. And we'll check that against table 7-2 to determine if it's acceptable. I'm not going to pull up table 7.2. In your mini design, you will need to check these values and make sure that they're in an acceptable range. And then the last, which some of you had questions about, was how to calculate the weir loading rate. So we need to determine a weir's length. Now we could do this in terms of determining the circumference, or let's just pick from table 7-3, gives us a weir loading rate of 180 cubic meters per day. So my weir length is equal to Q over my weir loading rate, which is 540 cubic meters per hour, 24 hours per day. Divide that by 180 cubic meters per day per meter, and that equals 72 meters. So that means I need to have a weir that's 72 meters long. Bear with me, we'll just quick look at this. And if we have a circular clarifier and said that the surface area is equal to 405 cubic meters, square meters, and calculate the diameter, that equals 22.7 meters. That means we have a circumference equal to 71.3 meters. Now, if we put the weir here in this center, and this is offset by 1 meter, that means we would have new circumference. This circumference here is equal to 65 meters. We just calculated that we need 72 meters of weir. So what that means is, so the water's entering in this from the center, and it's going to flow over this weir into this basin. Given that, we can either have a weir that goes all the way around, but is only notched on one side, or we can have we only need half the circumference and we can notch it on both sides. So we can have water flowing. In this case, water flows over both sides and we only need roughly half the length, or we still have this channel. So this is our launder, but we only have water flowing over one side, and we have it the full circumference. So that's what we mean by the weir loading rate. So we will stop there. Apologize for going a bit over. And we will start with filtration on Monday. And I'm happy to stay on and answer any questions that anyone has.